This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 28, Nuclear Magnetic Resonance Spectroscopy, Section 28.1, Intrinsic Nuclear Angular Momentum and Magnetic Moment. The nuclear magnetic moment, mu, can be calculated using this equation. Mu is equal to G sub n, this is the nuclear G factor, times E over 2 times the mass of the proton times this I in bold font. This I is the nuclear angular momentum. The magnitude of this I, this is a vector, so the magnitude of this I vector is the square root of I times I plus 1 times h. The z component of this I vector is from negative IH bar to positive IH bar. And then this part can be written as beta sub n over h bar. So this beta sub n is called the nuclear magneton over here. Beta sub n is E times h bar over 2 times the mass of a proton. H bar is the reduced constant. And also we can combine this G sub n, beta sub n over h bar. We get gamma. Gamma is a ratio. It's called magneto-gyric ratio. Gamma is G sub n times beta sub n over h bar. So it's this nuclear G factor. It's different for different nuclei times this beta sub n over h bar. This beta sub n over h bar is the same no matter what kind of nuclei you're looking at. So this gamma again is called the magneto-gyric ratio. So first I want to show you the table of several parameters for different nuclei. We use hydrogen NMR and carbon NMR commonly. So these two are the nuclear G factors for this one hydrogen and carbon-13. These two both have a nuclear spin quantum number of 1/2. So that means the Z component is negative 1/2 h bar or positive 1/2 h bar for the hydrogen or carbon nuclei. Again, we're talking about carbon-13. Carbon-12 has a spin number of 0. So we cannot do the NMR for carbon-12. There are some other different nuclei, phosphorus 31, hydrogen 2, nitrogen 14. So they have spin number of 1/2, 1, and 1. Those are the corresponding G factors. The larger the G factor, the larger the magnetic moment, and the easier for you to collect the NMR spectrum. This is the value of gamma. Again, gamma is just the G factor times this beta sub n. Beta sub n is the nuclear magneton divided by h bar. So those are the values of gamma in this unit. Those are gamma over 10 million in this unit. Again, typically the larger the gamma, the easier for you to collect the NMR. So that's why it's easier to collect the hydrogen NMR than to collect the carbon-13 NMR. Oh, there's another reason. So actually this is the main reason. The isotopic abundance of carbon-13 is only 1.1%. So if you're doing a NMR test of a organic compound, mostly you have carbon-12. They do not show up in the NMR spectrum. So that's why it is much more time consuming to get the carbon-13 NMR for your organic compound than to collect a simple hydrogen NMR. So this is the main reason. This is the second reason. The hydrogen has a larger magneto-gyric ratio. For hydrogen atom, its nucleus has a spin quantum number of 1/2. Therefore, the magnitude of its nuclear angular momentum is 1/2, the square root of 1/2 times 1 plus 1/2, and then times h bar. So really it's just the square root of 3 h bar over 2. its Z component can be just 1/2 h bar or negative 1/2 h bar. What is the Z direction? Well, it's arbitrarily chosen, but if you put your hydrogen nucleus in a external magnetic field, the direction of the magnetic field is your Z direction. If you have a H2 atom, deuterium, its nucleus has a spin quantum number of 1, so I think it's right here. Therefore, its nuclear angular momentum is the square root of 2 times h bar. So really, it's just square root of this 1 times 1 plus 1, and then times h bar. Its Z component is negative h bar, 0, or h bar. So you have 3 possible values for the Z component of the nuclear angular momentum of the hydrogen 2 atom. Section 2, 28.2. The energy of nuclei of non-zero nuclear spin in a magnetic field. So if you have a carbon-12, oxygen-16, they have 0 nuclear spin, you cannot collect the NMR spectrum for carbon-12 or oxygen-16. The energy of a magnetic moment or dipole mu in a magnetic field B0. So this is the strength of the magnetic field. Usually it's in Tesla. The energy is negative mu times B naught. And this mu is this gamma times m sub z times h bar. So I didn't put I here. I was used for the magnitude of the 3-dimensional nuclear angular momentum. But right now, since we applied a external magnetic field here, the direction is going to be defined to be the Z direction. So we're going to just focus on the Z direction here. All right, and then we have this. That's why we have this equation. This m sub z can be from negative I to positive I. For hydrogen, it's negative half or positive half. For hydrogen 2, it can be negative 1, 0, or 1. All right, so that's why for the hydrogen nucleus, it's this. Maybe I should say nucleus. Assuming there's no electron here right now. Additionally, you do have X and Y components. They are not parallel to the external magnetic field. So they will create a torque, and the torque is just mu cross product B0. So these two are vectors. So in here, this mu is a 3-dimensional vector. This B0 is also considered as a vector in this equation. This torque will lead to a movement of mu on the surface of a cone. So this motion is called precession. You can look at this wiki page to better understand precession. The frequency with which the magnetic moment precesses about the magnetic field direction is given by this. And this frequency is called the Larmor frequency. And you can read this webpage about Larmor precession. In the NMR spectroscopy, transition must be induced between 2 different energy levels. So when you apply an external magnetic field to a bunch of hydrogen nuclei, and some will occupy higher energy, some will occupy lower energy. So we'll be able to calculate the difference between these 2 energy levels. So let's calculate the possible energy levels for the hydrogen nuclei in a magnetic field of 9.40 Tesla. So 1 Tesla is 1 joule per ampere per square meters, or 1 kilogram per second to the power of 2 per ampere, or okay, whatever. There are many different ways to express this Tesla. I think this is commonly used. This is just 1 joule per SI unit of the magnetic moment. The energies of the upspin and downspin are given by this. So, or just use this equation coming from the previous page. I think it's right here. We're going to use this equation. The energy is plus minus half h bar times gamma magneto-gyric ratio times B0. B0 is the strength of the external magnetic field. All right, and use this equation for the hydrogen nucleus or any other nuclei with 1/2 nuclear angular momentum quantum number. All right, so over here. So this m sub z is plus minus 1/2. So you can use this plus minus 1/2 for carbon 13 as well. I think it's right here, or phosphorus 31. But if you have hydrogen 2 or nitrogen 14, well, you can't just use plus minus 1/2. You have to use -1, 0, and 1 as the z component. All right, get back to the equation here. We're going to do some calculations, numerical calculations. We just plug in numbers. Plus minus 1/2, I put it here, and this G factor, I put it in here. This is a G factor for the hydrogen nucleus. This is the charge of the electron. In Coulomb, this is h bar in joule times second, 2 times the mass of the proton, and then we have the magnetic field, B0. This is the strength of the external magnetic field. Okay, I did not keep track of the units of all the numbers, but I know I used the SI units for every single number. Therefore, in the end, this number, the result must be in joule, so I put a joule here. And the result is plus minus 1.326 times 10 to the power of negative 25 joule. All right, and what about the energy spacing? Well, it's just the energy difference between this plus and minus number. So it's 2 times this number, and I got 2.65 times 10 to the power of negative 25 joule. It's a very small amount of energy or energy spacing here. You'll see we can calculate the corresponding frequency of the electromagnetic radiation that corresponds to this energy difference. So basically it means when the protons jump from the higher energy level to the lower energy level, it's going to emit some electromagnetic radiation with a certain frequency, and that frequency can be calculated using this equation. So again, this delta E is the energy of the electromagnetic radiation divided by h. That will give you the frequency of that radiation. So energy spacing on top. So this is also the energy of the electromagnetic radiation, and then divided by h. So when you do this calculation, you'll get 400 megahertz. 400 megahertz. And we can also calculate the corresponding wavelengths. It's just c over the speed of light over the frequency. It's just 0.75 meters, so it's in the range of the radio waves. It's in the range of radio waves. Oh, if you still have those old style radios, you can take a look at their radio frequencies. Okay, you can take a look at their AM and FM radio frequencies and make some comparison yourself. Now we can also calculate the relative populations of the two states at the room temperature. We're going to assume the Boltzmann distribution. That means the ratio of the population is e to the power of negative energy difference over kBt. So I'm plugging in the energy difference here over kBt. Kb is the Boltzmann constant. Kb is 1.38 times 10 to the power of negative 23 joule per Kelvin. And the temperature, I'm using room temperature here, and I got ratio of 0.99936. All right, so what does that mean? So that means if you put many hydrogen protons in the external magnetic field of 9.4 Tesla, if you count the number of protons in the lower energy level, and you find there are 1 million protons that occupy the lower energy level, then there's 0.999936 million protons that occupy the higher energy level. Well, there's not much difference because it's just because this energy spacing is so small. This is much smaller than KBT. So again, KB is 1.38 times 10 to the power of negative 23, and temperature is 300 K. So KBT is roughly 4 times 10 to the power of negative 21. So you got 10 to the power of negative 25 on top, 10 to the power of negative 21 on the bottom. That's why you have a ratio very close to 1. Section 28.3, the chemical shift for an isolated atom. So if you place an isolated atom in an external magnetic field, the electrons around the nucleus can generate an induced magnetic field. The direction of the induced magnetic field of the electrons opposes the direction of the external magnetic fields. That's why you see a negative sign here. The equation is pretty simple. The induced magnetic field is negative sigma times B naught. And over here, sigma is the shielding constant. Shielding constant. Okay, this sigma is completely different from the sigma in a sigma bond. Okay, so it's completely different. It's over here it's the shielding constant. The value of sigma allows us to compute the strength of the induced magnetic field. Okay, and that's produced by the electrons. So now we have to make some corrections to the magnetic field felt by the nucleus. Now there's a correction here. Without the induced magnetic field, it's just B naught. With the induced magnetic field, it's going to be B naught times 1 minus sigma. This sigma is usually much smaller than 1. I think this sigma is usually 10 to the power of negative 5-ish. So this number is 0.99999-ish. All right. So you've got a induced field produced by the electrons, and this is the external field. The external field is much greater than the induced magnetic field, and these two magnetic field have the opposite signs. You can see the direction of the arrows. Okay, this arrow is pointing up, this arrow is pointing down. But I wish they could kind of make this a little bit smaller to reflect the relative magnitude of this B naught and B induced. Again, B naught is much greater than B induced. Section 28.4, the chemical shift for an atom embedded in a molecule. So now we're talking about real molecules. For example, organic molecules, ethanol or whatever molecules you're looking at using the MR spectroscopy. The frequency shift for an atom depends linearly on the shielding constant sigma. So this makes the MR a very sensitive probe around the nucleus with a non-zero nuclear spin. So again, if you have carbon-12 or oxygen-16, forget about AMR, okay? Because carbon-12 or oxygen-16 does not have a non-zero nuclear spin. So you can do H1, you can do carbon-13, you can do nitrogen-14. They have non-zero nuclear spin. So now two factors responsible to the chemical shift are one, electron activity. So this is pretty easy. So if you have a fluorine atom bonded to a CH3 functional group, this fluorine can withdraw electrons, right? So that means you have a lower electron density around the hydrogen nuclei in the CH3 functional group. And that means you have a smaller sigma, smaller shielding constant. And this 3 nuclei will fill a actually overall a greater magnetic field strength, because the magnetic field strength felt by a nucleus is the external magnetic field strength minus the induced magnetic field. All right. So when you have a fluorine atom bonded to a CH3, which withdraws electrons, and then you have smaller shielding from the electrons. All right. So you have a smaller induced magnetic moment. So this is pretty simple, and also you may have induced magnetic field of neighboring groups such as benzene or some other conjugated network that may affect the distribution of electron density. So most important factors are these two. I'm sorry. There are three. So this is the induced magnetic field of the neighboring group. So there are two factors embedded in here. So when you have a benzene, you basically have a electric current formed by the pi electrons. So that's a little bit different from just the conjugation in 1,3-butadiene. Now let's look at the chemical shift. Chemical shift is a dimensionless quantity delta. It's in ppm because it's usually small. If you don't use ppm, you'll have to say 0.000001, or 0.000007 for the hydrogen atoms in benzene. So that's why we use ppm. And the delta is 10 to the power of 6 times this is the frequency of the hydrogen nuclei of interest. And then we need a reference here. So we need a reference here. Typically, we use this TMS as the reference. What is TMS? TMS is tetramethylsilane. This is silicon bonded to 4 methyl groups. This is usually used as the reference for the hydrogen, carbon, and the silicon NMR. Silicon 29 has a non-zero angular momentum, nuclear angular momentum, so we can actually do silicon 29. And in that case, we also use TMS as the reference. I think the main reason is this is really, really stable, and it does not interfere with the peaks of your organic molecules. All right. So you do that, and then we have this nu. This nu is just B naught times 1. This nu is proportional to B naught times 1 minus sigma, and the new reference is proportional to B naught times 1 minus sigma reference. I think we did some numerical calculation of this nu a couple sections before. So this nu is proportional to delta E, and this delta E is proportional to the energy levels. The energy levels is proportional to this B naught, but this B naught is the magnetic strength filled by a free proton. Now it's not a free proton, it's surrounded by electrons, and when you have electrons, you need to make corrections to the B naught. Alright, it's now B naught times 1 minus sigma. Sigma is the shielding constant. So that means this nu is proportional to B naught minus the induced magnetic field. So this nu is proportional to B naught times 1 minus sigma. Let's see over here. Okay, this frequency is proportional to B naught times 1 minus sigma for the organic molecule of interest, and this new reference is B naught times 1 minus sigma reference. Okay, and this is for the hydrogen nuclei in TMS. And then we cancel B naught, and we simplify the top. The top is going to be just sigma reference minus sigma. The bottom is 1 minus sigma reference. Because this sigma of this TMS is so much smaller than 1, we can say this is approximately 1. Okay, so 1 minus 0.000001 is roughly 1. All right, so the sigma is the shielding constant. Sigma sub reference is the shielding constant of the reference molecule, and commonly we use TMS. Now I want to tell you how to do the calculations of the hydrogen MR, carbon 13 MR, and even silicon 29 AMR chemical shifts. It's pretty simple. We often use this method, this B3LYP method, and this basis set. This is a fairly large basis set, 6-311 plus GDP basis set for the calculation of organic molecules. And we use this method and this basis set to calculate the TMS first. We need to calculate the reference first. And then after we calculate the reference, we then calculate the molecule of interest, and then we take the difference. So you use your TMS value minus the value of the molecule of interest. All right, and then you will be able to get the value of delta in ppm. So this is how we do theoretical calculations of the chemical shift. So it's not just the molecule of interest. You have to calculate the reference TMS in this case using the same computational method and the same basis set. Oh, one more thing, TMS. This one does not belong to the tetrahedral point group. Okay, so I know this because I think the Gaussian company made a mistake of using a structure of TMS with a perfect tetrahedral point group, and it does not really have such a high symmetry due to the very large steric effect caused by the crowded methyl groups. So I don't think it's a tetrahedral group. It may not be even a T point group. I think it's probably a C1 point group without any symmetry. So when you do the MR calculation of TMS, make sure you distort your molecule a little bit so that you start from a structure with no symmetry. Section 28.5, Electron Activity of neighboring groups and chemical shifts. This is pretty easy. So if you have a electronegative functional groups bonded to your CH2 or CH3 groups, those electron withdrawing functional groups will reduce the electron density around those hydrogen nuclei. That will reduce the shielding constant. And when you reduce the shielding constant, so when you reduce this, you will have a larger delta. So when you have a smaller sigma, and then you will have a larger delta. All right? So there are two major factors here. So if you put, OH functional group, this OH withdraw electrons from OH here. It withdraw electrons from this 3 nuclei, hydrogen nuclei. NH2 also withdraw electrons from the 3 hydrogen nuclei. And for aromatic compounds, there's another reason. Again, the pi electrons on a benzene ring forms a electric current loop that will provide you a different situation regarding the induced magnetic field. Okay, and these two functional groups can attract withdraw electrons significantly due to two reasons. One is the electron activity, and two, the conjugation effect. So two reasons. This is the carbon 13 NMR. Carbon 13 NMR. Let's see. Again, those COO aldehydes, ketones, carboxylic acids, esters, they can reduce the electron density around the carbon 13 nuclei significantly in comparison to the reference. So the reference is TMS. So arbitrarily, we say the chemical shift of the carbon atoms in TMS is 0.0. Okay, this is a arbitrarily chosen zero reference. Section 28.6, magnetic fields of neighboring groups and chemical shifts. So if you look at benzene, so this is a benzene. So this is pretty interesting. You have a electric current loop that produces the induced magnetic field. So this is the direction. So you can see inside the benzene ring, the direction is opposite to the external field. But outside, this direction is the same as the external magnetic field. So because of this, this hydrogen atoms, they are outside the magnetic field. So they actually overall have a smaller sigma than many other organic compounds. All right, they have a smaller sigma. Okay, so there is, of course, shielding effect from the electron, but because of this electric loop, you have another factor here, which is in the opposite direction to the shielding effect, or the same direction as the external magnetic field. So this reduces the shielding effect. And when you reduce the shielding effect, I want to show you the equation. When you reduce the shielding effect, you have a larger delta. So that's why the hydrogen atoms on the benzene ring, I think they have roughly 7.2 ppm in comparison with 0.0 in TMS, or maybe 1 point something for a typical alkane molecule. Even if you put a chlorine atom, replace a hydrogen atom with a chlorine or even fluorine atom in an alkene molecule, I think your delta can go up to maybe 4 or at most 5, not 7. So benzene, you have 7.2 roughly, and this is because of this induced magnetic field from the electric current of the pi electrons. Well, same here, but in this case, you have hydrogen atoms outside the ring and hydrogen atoms inside the ring. So if you look at this picture, it's very clear. This effect is the opposite when the hydrogen is inside the ring versus the hydrogen atoms outside the ring. So if you look at the chemical shift for this 600 atoms inside this aromatic ring, they have a delta of -3 ppm. So it's really interesting here. So if this is -3, outside it's +7. That's actually a huge. Oh, outside, in this case, outside it's 9. This is a huge difference. 12 ppm is considered as a huge difference in the hydrogen NMR. the typical range for the chemical shift in the hydrogen NMR spectroscopy is between 0 and 10 ppm. So 10 ppm, either you have this kind of structure, aromatic structure, or if you have an aldehyde, okay, you have this RCOOH. That H has a very large chemical shift. And I think if you have a carboxylic acid, that H has a very large chemical shift, because the COO functional group can withdraw electrons from the hydrogen nucleus effectively.